Assalamualaikum. My name is Amir Rizlan bin Ismail, and our Group 11, will present about membrane separation. Okay, our group member consists of four, which is me, Muhammad Airi bin Alin, Muhammad Rafi bin Bahrain, and Bradin Inchana Anak Suel. Okay, I will present the introduction of this problem-based learning. Membrane separation is a widely used technology for separating different components or solutes in a variety of industries. Membrane separation also allows molecules that are smaller than the membrane pores to pass through while rejection bigger ones. Membrane separation also has several advantages such as high separation effectiveness, low energy usage, and simplicity of operation. This technique have also attracted a lot of interest since they have the potential to solve many industrial and environmental problems. Our objective from this problem-based learning, the first one is to identify the industrial process of membrane separation. Number two is to understand the principle of membrane separation and how the unit is operated on a day-to-day basis. And the last objective is to discuss the application of membrane separation used in the industry of process plant technology.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Rafi bin Bahrain. My matric number is DD200115, and I will continue the presentation and I will talk about the principle of membrane separation. The principle of the membrane separation is based on the difference in permeability of materials and substance. The driving force for the separation is given by the difference in the pressure, concentration, and electric potential. And the figure below shows the pressure driving membrane separation mode depending on the size of separation target. So this is the figure showing the pressure driving membrane separation modes. The type of pressure driven membrane separation techniques are categorized according to membrane pore size, which in turn dictate the degree of separation achieved. The categories are microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. Microfiltration lies on the upper end of the spectrum of pressure-driven membrane techniques, with membranes containing the largest pore size of the aforementioned process. It is capable of separating suspended solids within the range of 0.1 up to 10 micrometer, and is often used as a precursor step to downstream filtration application in order to achieve the desired degree of separation within a given feed stream. Due to the larger pore size of microfiltration membranes, many of these processes are capable of being run at lower pressure than those with membranes containing smaller pores. Common microfiltration applications involve the separation of large macromolecules in clarification steps, such as in the removal of bacteria from cellular broths and in fat removal process in daily industry. For ultrafiltration, within the family of pressure-driven membrane process, ultrafiltration lies between microfiltration and nanofiltration in terms of pore size, which can range from 1 to 100 nanometer. This size range allows for the concentration of high molecular weight proteins, macromolecules, and other small suspended solids. In contrast to MF, ultrafiltration membranes are categorized with respect to their molecular weight cutoff, their ability to retain a molecule of a given size, rather than by the size of their pores. Nevertheless, the pore size range of ultrafiltration membranes make them well suited for use in a wide variety of ultrafiltration applications across multiple industries. In the automotive industry, ultrafiltration is used in the recovery of undeposited paint for reuse in the electrocoating process. In the beverage industry, it is used in application ranging from the concentration whey protein to the clarification of fruit juice. For nanofiltration, in contrast to NF and UF, in which solutes are separated according to size, both size and charge play a role in nanofiltration separation process, with a pore size between 0.1 to 10 nanometer. Nanofiltration membranes are capable of retaining low molecular weight uncharged solute, such as sugar and other organic molecules. Nanofiltration membranes are also retain charged species, such as polyvalent ion and large monovalent ion, where smaller monovalent species pass through. Application for nanofiltration membranes range from the removal of natural organic matter in wastewater treatment, hardness reduction in water purification, and whey demineralization in dairy processing. And for the reverse osmosis, the membranes contain the smallest parts of the pressure-driven membrane process and are capable of retaining all dissolved particles within a feed stream, including monovalent ion. This degree of separation results in permeate consisting of a pure solvent, which in many cases is water. Separation using reverse osmosis is accomplished not only through size exclusion, but utilize a diffusive mechanism as well. The necessity of overcoming the osmotic pressure, in addition to the extremely narrow pore size found in reverse osmosis membrane, result in reverse osmosis process requiring higher pressure than those previously mentioned. The most common application for reverse osmosis are in the preparation of drinking water and beverage concentration. The membrane principle is quite simple. The membrane acts as a very specific filter that will let water flow through, while it catches suspended solid and other substances. There are various methods to enable substances to penetrate the membrane. Examples of these methods are the application of high pressure, the maintenance of a concentration gradient on both sides of the membrane, and the introduction of an electric potential. Membranes occupy through a selective separation wall. Certain substances can pass through the membrane, while other substances are caught. Membrane separation can be used as an alternative for flocculation, sediment purification techniques, adsorption, extraction, and distillation. There are two factors that determine the effectivity of a membrane separation process, which are selectivity and productivity. Selectivity is expressed as a parameter called retention or separation factor. Meanwhile, productivity is expressed as a parameter called flux. Selectivity and productivity are membrane dependent, as shown in this figure. So that's all from me for the principle of membrane separation. Thank you.
Assalamualaikum. I'm going to present about the equation. The following direction of the gas stream is parallel and in the opposite direction on both sides of the membrane. Below is the figure of the gas streams. The feed with a specific flow rate, which is QF, enters the unit and is divided into two streams, which is QP on the pyramid side and Q0 leaving on the residual side. The streams have a mole fraction of SF, YP, and XO respectively. Next is we have to find the overall mass balance. Formula is QF equal QP and plus Q0. QF is the feed flow rate, Q0 is the residual flow rate, and QP is the pyramid flow rate.
Then we have to find the component balance by using the formula below, which is QF times XF and QP YP plus Q0 X0. The stage cut is defined as theta equal QP over QF equal QF minus Q0 over Q0. The ideal separation factor selectivity is alpha equal PA over PB. PA is the permeability of gas A and PB is the permeability of gas B. Next, we have to find the pressure ratio. It is PI over PH. Parameter PI is the low pressure on the permit side and PH is the high pressure on the feed side. By using the finite difference method, FDM, taking the increment area delta AM, the mass balance of both strings can be written as delta QP equal Q in over Q out. Delta QP, QP and Q out are the flow rate of the permit flow of an increment. Flow rate entering the increment and flow rate leaving the increment respectively. Next is additionally the value of Y out from the formula above, which is permit at the end of the increment is calculated similarly by using X out for X in. The balancing A, we use the formula below, delta QP, Y prime AV equal Q in, X in equal minus Q out, X out, where Y delta AV equal Y in plus Y out over divided by 2. Next is splashing out from equation 6 and 8 from the formula below. Using equation 10 and 11, the increment delta QP are added to obtain QP and Y is calculated for each AM or delta AM increment up to SF at the feed inlet by using the formula below. Next is the ideal counter current flow, but can be calculated by using the formula below. Then the average driving force is using the formula below. Solving for the delta AM equal to delta QP Y prime AV over PA divided by T times PH times Q minus lambda Y prime times AV. Starting at XF, delta AM is calculated for each increment to obtain sum total of delta AM versus X. For the membrane separator performance modeling, the known variable are the feed composition, feed load rate, and feed pressure, membrane permeability, permit pressure, and residual mole fraction. The algebraic equation are solved by using FDM, also known as the stepwise increment method. In the present study, the differential equations are not involved, which prevents the mathematical model from using L'Hospital's rules, Gears BDF method, and the secant method.
Okay. Good morning. My name is Brandon Inchana, and today I'm going to present a discussion on a research about gas separation of hydrogen gas as clean fuel using a membrane, polymer membrane to be exact. Gas separation utilizing membrane separation show a promise of sustainable technology through its purity of gas production, like, for example, a hydrogen gas. See, hydrogen gas as a clean fuel can pare down to the energy generation from a burning coal fuels. As we know, crude oil accounts for 97% of all fuel resources throughout the world, producing around 25% of the world greenhouse gas emission. Therefore, if we need to reduce the carbon emission throughout the world, we need to create a method that can separate hydrogen gas from ammonia or any solute that are most economical and secure way to efficiently avail hydrogen gas as a fuel, where polymer membrane play a crucial role because of their low cost and capacity for hydrogen absorption as well as selectivity. In here, we use polymer membrane as a membrane to synthesize and use a different variety of membrane for separation of oxygen and nitrogen from air, or carbon dioxide to CH4 from landfill, biogas or natural gas, or carbon dioxide and nitrogen gas in power plant, or a hydrogen gas recovery in ammonia manufacture as a water gas shift reaction, and even olefin paraffin separation in refinery. Membranes or polymer membranes can be prepared from different polymers such as a polycarbonates, polyamides, polyamides, polyetheramides, or polysulfone by various techniques. This goes to the theory of gas permeation, or using partial pressure gradient, which is the total of pressure and mole fraction, and also most membranes used for gas separation are non-porous. However, there are mass transfer through porous membranes such as Knudsen diffusion. Here is we can see the diagram shows how the principle of gas permeation and separation. As you see here from the left are the feet, and we can go through a membrane. In this case, it's hollow membrane, and come out is retention and concentrated. And here is the diagram for Knudsen diffusion, molecular sieving, and solution diffusion. All right. Here is the schematic diagram for the module of the membrane, polymer membrane. As you can, the first one schematic is a plate and frame module, which are earliest types of membrane assembly. They are the closest to common laboratory setups. The membranes, feed spacer, and product spacers are layered together like in a sandwich between two plates. As for spiral wound module, which is the B, is a plate and frame system wrapped around a central perforated pipe collecting permeate. The spacer is placed between the membranes to avoid contact of feed and permeate, and also to provide clearance for gas to interact with membrane. That was the B. The C is the hollow fiber. The hollow fiber consists of thin, fine capillaries collected together and made into a bundle. This bundle perfectly parted on both the ends to arrest any leakage between feed and permeate chamber, and then placed in the housing. And lastly, here is the tubular membrane module configuration. Okay. There is the several factors that influence membrane's performance. The composition of the feed has a significant impact on the permeation characteristic, since the diffusion of the gaseous components in the membrane depends on their concentration or solubility. Since the driving force in gas separation is the partial pressure gradient across the membrane, generally speaking, solubility declines as the temperature rises and diffusivity rises. At a higher temperature, a membrane procedure with extensivity at room temperature may produce pore separation on the membrane sides. That's all from me. Thank you.
To conclude, membrane separation is an effective and adaptable technique that has transformed several sectors. Membrane separation has become a popular option for separating and purifying substances because of its energy efficiency, scalability, and environmentally friendly operation. We may anticipate more developments in membrane composition and structure as technology develops, resulting in separation methods that are even more effective and efficient. That's all from us. Thank you.